So just in case you guys hear banging during their presentation, they have just essentially handed the judges a drum, or 2 drums, I guess, 3 drums. I'm seeing lots of things. So if they decide to play during the middle of the presentation, you know why. It's all your fault. All right, we're getting ready to kick it off here in 10 seconds. You ready? All right, and we are back with Northwestern University and their concept titled Metals. Take it away, Northwestern.
Hello, good afternoon. My name is Trevor Rabbit, and as a team lead, I'm proud to present Metallic Expandable Technology for Artemis Lunar Structures, or METALS. I'm joined today by an ambitious team of engineers that redefined inflatables, as you will learn today, through over 300 inflations. Currently, state-of-the-art inflatables, which are polymer-based, maximize deployed to stowed volume, minimize mass, and are considered a low-swap technology. This makes them potentially great for habitats, towers, transportation, and shielding.
However, the harsh environment on the moon makes it very difficult for long-term use of polymer-based inflatables. First, the lunar dust is very abrasive, as seen on Apollo 12 with the damage to the spacesuits. The large temperature fluctuations can cause damage to material properties, as well as change in the internal pressure. The radiation on the moon can cause damage to the covalent bonds in the polymers, weakening them. And lastly, micrometeorites are very difficult to repair. On the other hand, metals are very resilient in this environment. First, they're very resistant to abrasion, making them ideal for cases such as machine tools. They have a very high operating temperature window in cryogenic and in high heat for the case of stainless steel. They are very resistant to radiation, use in nuclear reactors for upwards of 50 years. And lastly, they're very repairable via TIG welding or other welding methods. So how is a metal inflatable different from a traditional inflatable? Well, a traditional inflatable relies on the internal pressure for its structure, and if it is popped, then it loses that structure and can no longer hold its weight. However, the metal inflatable is plastically deformed, meaning it's permanently deformed. If it were to be punctured by a micrometeorite, for example, it will keep that structure, and then someone could go and repair that hole.
So now you might be wondering, how do you make a metal inflatable? Well, we're going to break it down for you into 3 easy to understand steps. First, 2 identical sheet metal geometries are cut out either using a water jet or a laser cutter. And then the valve is welded onto one of these sheets, and the edges of the 2 sheets are welded together. Now we have our completely sealed 2D geometry that is ready to be inflated with air or another fluid. As you can see in front of you, judges, you have some smaller inflatables, but the real question is, can we make these large? And yes, we can. And in fact, here's a 48-inch inflatable being inflated.
The simplicity of metals manufacturing process stands in contrast to the highly specialized and complex manufacturing of traditional polymer-based inflatables. This is critical for reducing the times and costs required for production, but more importantly, it allows the accessible entrance of a variety of commercial suppliers, as anyone with access to the machine tools in a traditional machine shop, even an undergraduate lab, can make a metal inflatable. Combined, these effects can enable the rapid optimization, scalability, and flight qualification of metals. Within our project alone, we've managed to make over 300 different inflatables, and with additional commercial involvement, we see this as a rapidly iteratable solution for making this a high-value application within the near term of the Artemis program. We see a variety of potential applications for metals for the Artemis program, whether it's deployable structures or pipes for transporting cryogenic fluid. But one application we see as particularly high value is that of deployable cryogenic storage, something you're going to need if you want to store large volumes for refilling launch vehicles on the lunar surface from ISU-derived propellants. But such a cryogenic storage solution needs to meet 2 criteria. The first is it needs to be deployable. If you have rigid metal or composite tanks, which would be the current state of the art in cryogenic storage, it's an inherently volume limited solution because a lunar lander can never deliver more cubic volume than its own volume. An inflatable, however, can meet this need. Additionally, that cryogenic solution needs to withstand its material toughness at the storage temperatures. Most polymers lose their toughness at cryogenic conditions, but metal is already the material class of choice for cryogenic storage. Combined, we see this concept of a metal inflatable as both advantageous and even an inevitable solution for the requirement of scalable cryogenic storage on the moon.
Once modules are manufactured, they're densely stacked within the payload of a lunar lander, just as sheet metal would be packed. Then they're offloaded from the lander and inflated with gas under direct sunlight. This increases ductility and toughness during inflation. Finally, gas is recovered and used to inflate other modules.
Once deployed, the modules can be lowered into holes dug into the lunar surface by autonomous excavators, connected to a fluid distribution network, covered in regolith, and then filled with the fluid of choice. Bearing under regolith provides a number of advantages, such as protection from the lunar day-night fluctuations, and as much radiation and micrometeor protection as you could want. You just bury as deep as the level of protection required. Most importantly, that regolith provides a lot of exceptional thermal insulation, so you can store large volumes of cryogenic fluid with minimal energy input. Additionally, all of those benefits of the regolith come with zero payload mass penalty. The regolith is already abundant on the moon, and you don't need to transport it. Additionally, the optimization of metals can happen with extreme efficiency because the design space is extremely simple. All you have to do is select your alloy of the sheet metal, the pressure at which you inflate, the thickness of that sheet metal, and then the 2D shape that's cut from your sheet metal stock. Combined, you can choose those variables to optimize our key performance parameter for metals, which is the cubic volume of deployed fluid storage you can provide on the moon per kilogram of sheet metal brought to the moon, under the constraint that that given design can meet the storage requirement or the storage pressure requirements of a given cryogenic need.
Early on, we discovered that thin metal buckles as it's inflated. We must control this buckling if we want to create reliable inflatables. You can see on the screen 5 pentagons that were manufactured in exactly the same way. They buckle differently, and we actually have an octagon right there that also buckled different than those. So if we're to control this buckling, we've got to control it. So we came up with what's called the sinusoidal edge circle, or SEC as it's referred to throughout the presentation. This SEC guides the buckling and minimizes stress concentrations. This optimized shape reliably inflates each time. You can see our SECs at that end of the table. Each time we inflate those, we get the exact same behavior.
Now that we understand our design, we need to select a bearing depth. We first considered the weight of regolith on the inflatable, but understanding that the pressure of the regolith will counteract the internal pressure of our inflatables, we understand that stress will be reduced as depth increases, and for this reason, we considered it a non-factor. Instead, we focused on the dampened thermal fluctuations as depth increases. And as you can see with that large arrow, at a depth of 40 centimeters, temperature fluctuations are within 10 Kelvin. This limits exposure to high daytime temperatures, and for this reason, we selected 40 centimeters as our minimum buried depth. Now, we have to characterize regolith thermal performance. We first attempted an experiment where we buried a low temperature inflatable under regolith. Measuring the temperature versus time, we tried to characterize the heat transfer, as you can see on the right. But we ran into some setbacks, and we realized variables were difficult to control and also expensive, such as initial temperatures and applying a vacuum to an environment compatible with regolith. Instead, we opted for simulation using finite element analysis that gave us greater control over these parameters of the mission scenario. We modeled it for the worst case, including constant sunlight, perfect regolith solar absorptivity, and the minimum expected fluid temperature storage of 70 Kelvin. Here you can see our 2D axisymmetric thermal model. In the top left, you can see the ellipse represents our inflatable buried underneath the lunar surface. The solar flux is applied at the top of the model, and a constant 70 Kelvin is set at the inflatable. Simulation results can be determined in two ways. Cooling required for inflatable versus depth shows that increasing depth reduces cooling requirement. Specific cooling required versus depth shows that larger tanks reduce specific cooling requirements. And in fact, at a depth of 45 centimeters and a diameter of 4 meters, we can store liquid oxygen for under 2 watts per cubic meter. This can store all of Starship HLS capacity for less than 2,100 watts. This shows that bearing metals modules at least 45 centimeters deep is more than sufficient to insulate cryogenic fluid.
Further methods for feasible cryogenic storage have been identified to add flexibility to the metals mission scenario, but more testing is necessary. Permanently shadowed regions are much colder than cryogenic temperatures, which means sustaining cryogenics at the liquid state requires active heating. Now, thermal management can be reliably accomplished through resistive heating directly with the modules. Alternatively, fluid can be stored at the stolid state, which will not only increase storage density, but decrease energy consumption. Outside of PSR, where cooling would be needed, a lightweight, low-emissive shaded tarp could be constructed above buried modules to essentially block regolith absorption of solar flux, which could reduce temperatures substantially, and therefore the rate of heat transfer.
To achieve TRL4 and TRL5, we studied the scalability laws of the metal through rapid iteration and manufacturing. We evaluated the reliability of our manufacturing methods, and we evaluated the inflatable design within a variety of lunar conditions. At this point, we will now move on to our testing and verification results for each of the 8 subsections.
The first experiment, standardized inflation pressure, validated the reliability and consistency of 3 geometries, the pentagon, octagon, and SEC. 15 inflatables of 12-inch diameters, all made of 1mm 304 stainless steel, were inflated to pressure using a water displacement method to collect their volumetric expansion data. For pressures beyond 150 psi, a pressure washer was employed. From the graphs above, it can be seen how the pentagon and octagon have inconsistent deformations with their various volumes and failure pressures. This was mainly due to buckling occurring at 1 or even 2 sites. Notably, the SEC differs from those geometries. Here we can see how it has a consistent deformation with a high slope before 50 psi and plateauing afterwards. The SEC was able to achieve its maximum volume at similar pressures as other geometries, but withstand maximum pressures that are nearly 10 times greater. All samples followed the same deformation behavior due to the lack of buckling, demonstrating its consistency, reliability, and durability.
We analyzed the effect of a module's shape, material, and thickness on its deformation and inflation pressure to find the optimal combination of design parameters. A total of 24 samples were evaluated, utilizing 2 thicknesses, 1mm and 2mm, 2 materials, stainless steel 304 and low carbon steel 1008, and 4 geometries, including the SEC, pentagon, hexagon, and octagon. The same procedure as the previous experiment was followed. In terms of thickness, 1mm thick modules demonstrated bigger expansion but lower burst pressures. These were observed to buckle more easily, thereby bursting, leading to failure at around 25 and 50 psi. In contrast, 2mm thick modules resisted pressures exceeding 125 psi, highlighting its superior longevity and pressure tolerance. Therefore, an increase in thickness raised failure thresholds by absorbing more stress before yielding, but reduced volumetric expansion. Notably, the SEC geometry remained unchanged by thickness. As evidenced by the figure to the right, this geometry demonstrated initial deformation rates, just like 1mm thick modules, but survived pressures higher than at 125 psi, like 2mm thick ones. Material selection was found to only influence burst pressure. While both low carbon steel and stainless steel 304 produced similar final volumes, stainless steel 304 demonstrated a maximum burst pressure of 616 psi, highlighting its superior longevity and pressure tolerance. Regarding geometry, pentagons achieved the highest deformation by lowest burst pressures of around 70 psi. In contrast, octagons and SECs achieved similar deformation, but while the former burst at 140 psi, the SEC, as mentioned previously, survived pressures up to 600 psi. Combining the conclusions from standardized pressure and deformation versus pressure testing, it is evident that the SEC is the most optimal geometry for metals. Its sinusoidal crescent troughs were found to distribute stress effectively, minimizing localized buckling and enabling higher pressure tolerance.
The next step to elevate our design to TRL5 was vacuum testing. This allowed us to test our inflatables in relevant lunar condition while verifying that pressurizing in a vacuum would not affect performance, as you can see in the video. For each of the free tests conducted, we placed the inflatables in a vacuum chamber and pressurized them with argon gas while the chamber was brought to a pressure of 0.05 torrs. For each inflatable, we also pressurized them outside of vacuum for comparison. On the lower right, you can see an inflatable that was vacuum tested, and to its right, you can see the same geometry inflated outside vacuum. As you can see, there were no differences in the post-inflation geometry, nor there were any in the inflation behavior. Overall, we verified that metals inflatables maintain structural integrity as they did in atmospheric pressure.
To validate metals' pressure holding capability, the SEC and pentagon geometries were inflated to 22 psi and stored without manual depressurization for a 2-week period. Daily pressure checks revealed that while the SEC developed pressure leaks along the Teflon tape sealing the pressure gauge, the pentagon maintained 22 psi throughout the 14-day trial. This demonstrates that metals can effectively hold pressure when properly sealed.
We conducted 2 experiments with identical inflatables to test if they are reliable under cryogenic conditions and to determine the ideal inflation temperature. For our first experiment, 3 inflatables were inflated at different temperatures to identical pressures before each was nano-indented at room temperature to determine post-inflation yield strength. The inflation heights were then measured as a proxy for comparing the changes in volume. Our results showed that inflation heights and burst pressure decreased with temperature, but material hardness did not change. For our second experiment, 2 inflatables were pre-inflated to 85 psi at room temperature before one was cryogenically cooled. Both were then inflated to 150 psi to test if temperature affected inflatable failure. Our results showed that cryogenic pre-inflated inflatables resisted changes in volume, but showed no change in burst pressure.
Overall, we recommend inflating our inflatables during the lunar day or after warming them up. In our second experiment, we demonstrated that such pre-inflated inflatables are reliably resistant to changes in pressure and unlikely to fail in the cryogenic applications we expect, where the storage pressure is likely not that much higher than the inflation pressure. Also, both experiments demonstrated an undesirable decrease in inflation volume with decreasing inflation temperature, so inflating at warmer temperatures would negate this. And finally, the only inflatable that failed throughout all of our testing was the one inflated at the lowest temperature. Now, if we inflate while it's warm, we negate this. The reason why we think colder inflatables are more likely to fail is because colder metals are less able to deform to relieve the stress that is placed on them. If you look at this weld picture, you can see that the weld pocket increases in size for room temperature inflatable from about 2 microns to about 50 microns. But importantly, the end is blunted, which means the crack is less likely to spread and cause failure. For this cryogenic sample, you can see that while the weld pocket increases less in size, the end is unblunted, which is likely to fail.
Two methods were developed as repair solutions for punctured metal modules, such as those caused by high-velocity micrometeorites. A 0.223-inch hole was drilled onto the inflatables to simulate a puncture and fixed with one of the two solutions. The first is the solid-state solution, consisting of TIG welding a 1 by 1 inch patch over the puncture region, as you can see on the top right.
Meanwhile, the liquid-state solution applied a filler in a spiral pattern using MIG welding. Compressed air was introduced into both samples, checking for leaks with water and soap. Both solutions effectively sealed the punctured regions with no leaks detected at 55 psi. The solid-state solution is most suitable for larger punctures, while the liquid-state solution is preferable for smaller ones.
For the reliability testing, we used X-ray microcomputed tomography to identify internal defects like voids or cracks that might weaken the structural integrity of our welds. Sample 1 was made of carbon steel and was cut from a module welded by us, whereas samples 2 and 3, made of stainless steel 304, were cut from modules professionally welded by IMS manufacturing. We generated high-resolution images which were compiled into 3D renderings, which can be seen here, and were analyzed using the Amira software from Thermo Fisher Scientific to identify defects like cracks and porosities in the welds. Our analysis revealed that sample 1 exhibited a porosity defect at the joint, which is just bubbles, air bubbles trapped in the welds, and it can be visualized in these red circled areas. This highlights the risks of inexperienced welding, such as breaches under pressure or void-induced stresses. In contrast, samples 2 and 3 showed no detectable defects, suggesting that professional welds have greater consistency in their internal structure. Overall, high-quality welding is crucial for safety in extreme environments, and if it's done professionally, we expect the welds to be reliable.
Strength testing aimed to determine the maximum low capacity and reinflation capabilities of metal modules. 5 modules, all of different geometries, thicknesses, diameters, and materials, were inflated and compressed while depressurized using a universal testing machine. Those without any failures at the welds from the first inflation were then compressed and reinflated. From this graph, a 12-inch octagon and 18-inch SECs with 2 millimeter thicknesses had significantly higher low capacities than their 1 millimeter counterparts for stainless and low-carbon steel, both surpassing 4,000 pounds. From a 6-inch, 1 millimeter stainless steel pentagon, it was revealed that repeated compression inflation cycles could be achieved, as seen from the graphs, with slightly higher low capacities and inflation highs each time. However, this could result from material weakening due to crop propagation or void expansion. Nonetheless, this still highlights the great strength that lies within metal inflatables and their potential for repeated use.
We have identified several critical areas to research further on the path to flight for metals modules. These include conducting additional reliability tests such as vacuum and ultrasonic weld tests, establishing batch standards for weld penetration to ensure module integrity before launch, and scaling up to larger, thicker modules to achieve full operational capabilities. Validating patch welding techniques with a Lunar welder to repair damaged modules, optimizing thermal management for cryogenics using reflective coatings or storing in permanently shadowed regions, developing an installation plan that ensures compatibility with Artemis infrastructure, and finally, designing custom pipe fittings to increase the stacking efficiency of metals modules.
During the project, we've demonstrated the scalability of metals from modules of diameter less than 8 inches all the way up to 4 feet in diameter. The true lunar use case will require modules even larger than that, but the path forward for scalability is very promising. First, our experiments showed that the deployed volume of the SEC modules scales as the initial diameter cubed, unsurprisingly, but surprisingly, with no significant dependence on the sheet metal material and thickness, showing how the SEC shape guides the deformation into a self-similar topology regardless of the scale. Additionally, our best SEC inflation experiments demonstrated pressurization up to 54% of the material limit that we would estimate from hoop stress theory. If we extrapolate that to larger sizes, we can estimate that the specific storage capacity of metals can be such that one Starship can deliver enough modules to carry the fuel propellant capacity of 5 Starships. If the state of the art for your comparison is rigid metal or composite tanks, then this would represent a 5-fold improvement over the state of the art. However, if you incorporate additional improvements in your weld efficiency and weld quality, combined with higher performance aerospace alloys like titanium and aluminum based, or improvements in the SEC shape to further reduce the stress concentrations, you can push this scalability to even more improved levels.
In the past 9 months and over 300 inflatables later, we have demonstrated affordable, accessible, and reliable processes for manufacturing and repair. We have demonstrated scalability up to 48 inches in diameter. We have optimized the sinusoidal edge curve, or SEC, and finally, we assessed our performance under relevant lunar conditions. We can confidently say that metals is a high-value, low-risk, low-cost inflatable solution for scalable, sustainable lunar infrastructure within the decade. Thank you.
Thank you, Northwestern. We'll now get into the Q&A session with the judges, starting with Doug.
So I've spent most of my career telling people that inflatables are made of fabrics and soft goods, so I really don't appreciate the metallic inflatable. But I think you've convinced me that it's feasible and it could work. So I think you guys did a really good job. And I'm impressed with the 300 different things that you welded together and inflated. That's awesome. So my question is related to sort of what you were just talking about in terms of packaging and how you can actually stack a whole bunch of them up or something like that. So right now it looks like you're showing a lot of your designs are flat tanks, right? And so if you have a 4-meter diameter tank, then you need a 4-meter amount of space or a rocket or something that's that big. So I'm wondering, have you thought about other solutions for packaging that you can get like more volume, but still within a small launch or landing envelope, as opposed to needing that large scale?
Yes, so the flat stacking we found was relatively straightforward because it's flat sheet metal, but other stacking or packing methods, there's rolling, which is something we explored a little bit, where you take your long pipe and you just roll it up like a fruit roll up. So that's another possible application.
In terms of the scalability, one advantage as well is that you can always choose to have a smaller initial diameter and just have more tanks until that desired capacity is reached. If you're targeting Starship HLS, then your absolute limit for the flat stacking case is a 9-meter diameter, but you can always have less and more. The only hindrance there is your ConOps become slightly more complex because you have to deploy more modules and have more connections between the tanks to your fluid source. However, that does also add additional reliability because if there ever is a failure and there's fluid loss, a greater number of smaller modules results in less overall fluid loss in the case of an accident.
Thanks.
Yes, hi. I'd like to commend you on a great job. So do you have any thoughts on, welding hasn't been done on the moon. So do you have any thoughts on how do you plan to mimic lunar welding on Earth? If that's what you want to do. So welding hasn't been done on the moon, on the lunar surface. In your path to flight slide, you mentioned lunar welding. That is something you want to test. Any thoughts on how do you plan to mimic that on Earth?
Yeah, so we did some research and we saw that there is actually a NASA-funded research on the Lunar Resources PE 3D welder that actually has been welding in a test environment in a vacuum. So we'd be excited to explore that technology and see if it would apply well to our inflatables.
And that would be mainly for repairing or connecting, whether you want to connect modules on the moon. The main use case we see, though, is manufacturing them on Earth and sending them up, testing them on Earth, making sure they're good, and then sending them up. Did that answer your question?
Yeah, partly. Thank you.
Okay.
think on like your last slide or something, you said you optimized that scallop design. All right, there's three variables. There's the radius, the overall radius, the smaller radius, and the frequency. Obviously, the overall radius is probably set by how big of a tank you want, but how did you optimize those other two variables?
Yeah, that's a great question. So we did through both a combination of real-world experiments and also a lot of finite element analysis. So we developed a couple of tools that will allow us to automate the entire simulation workflow, and we simulated over 1,000 different design points with those different parameters. Also, something to consider when optimizing the geometry is that we did not stop just at the SEC. So if we consider any single edge profile, it can be thought of as a Fourier transform of a bunch of sum of cosine and sine curves. We did consider also optimizing all of the different amplitudes for all of those different curves. We did find, however, that as we added more and more terms, the complexity of the geometry made it a lot harder for ANSYS, which was the software we used to actually converge to a solution. So keeping it constrained to either a single cosine curve or also another shape that we later considered, which added a fourth factor that we could also optimize. Keeping it under those constraints allowed us to simulate a large variety of different design points while still ending up with a valid solution that we could confidently say is an optimal point given the limitations.
On one of your earlier slides, and then the inflation of the 48-inch module, in the initial slide that I was talking about, the graph of kind of the volume of each of them, there's some variance in kind of the SEC as far as from one to the other. And then on the 48-inch module, in the image, it looked like there was some kind of indentations a little bit more in different locations. The question is, what do you feel is the consistency of the volumes that you're going to get? And was that error, or that difference kind of an early state of kind of the shapes, and was that improved as you went on? Any thoughts there?
Yeah.
So in terms of volume, there was some inconsistency in our initial setup. It was conducted with two separate parts. So there was the water displacement, which was very limited to our air compressor that only got to 150 PSI. And the setup itself, we're afraid there might have been some inconsistent with how airtight it was. So the water flowing out may not have been as precise as we would have hoped for. But one way to recheck that was using the pressure washer method, which also allowed us to get to higher pressures. And with that, we would inflate it with pressurized water, disconnect it, and weight it so we could get the internal volume mass, and we're converted to that volume. So despite some of those lines kind of showing like some differences and inconsistency, they all followed the same behavior, which is, that high slope and then some plateauing. And even though, there is some gap of almost 100 millimeters. It could have been a result of that inconsistency, but they do end up in that almost 4,000 millimeter margin. And in terms of the 48-inch.
And to emphasize that gap in that data comes from our first method of measuring that mass, which is displacing water, that had the advantage that we could continuously measure how the volume is changing with pressure versus our alternative method of inflating, removing the pressure, filling with water, and placing on a scale, where we can get very accurate measurements, but it's not continuous if we want to truly study the pressure versus deformation curve. And so the accurate numbers that we used for our final inflation volume come from that second method where we're weighing the actual water and getting a very confident estimate of that volume.
Were they more consistent with that method?
Also, talking about maybe a little bit more about the buckling and different variations in volume across different inflatables. So as you can see, we mostly worked with 12-inch inflatables just because it was easier to manufacture and just constraints that we had in order to make a large amount of tests. So since we worked mostly with 12-inch inflatables, we were able to get it down like almost to a science, like on this OTR shape with this frequency was the one that produced the most consistent results. We weren't able to do that many 48-inch inflatables. We only did one OTR. So definitely path to fight, and we have a methodology down so we can improve and optimize the parameters given the diameter constraints. So working more with higher diameter inflatables will definitely give us a little bit more consistency.
So it is an open question. If you were to increase the diameter of this, does the SCC geometry still work to remove buckling?
Yes, definitely. At least the parameters, whether the parameters stay constant as we increase the diameter, so whether the frequency stays constant or the percentage of the small radius and the large radius, those types of relationships, whether they stay constant under like larger inflatables, those are still questions that need to be answered. But further testing under those larger diameters could definitely answer those questions.
There is just one small point that I want to drive home here, which is with the SEC, what we did, especially in my testing, deformation versus pressure testing, was to see how the shape would deform regarding pressure when it comes to thickness, material, and geometry. When it came to scalability, I believe that we needed to further research that area. We were constrained by size up to a maximum of 48 inches for the SEC to see how it would affect inflation. We conducted this inflation for the 48-inch SEC to see whether it would be feasible. But further research is recommended there. With the SEC, what we confirmed with our testing was how it would perform in general terms, meaning it would show high initial deformation and then plateau at a specific volume. And that's what we can trust, the safety factor and that volumetric expansion.
Yeah, just real quick. One thing to know, you're talking about pressure testing and stuff. GCD had a project, composite overwrap pressure vessels. In order to qualify it for flight, we did hydrostatic burst tests. And so we did, the requirement is 100 hydrostatic burst tests, and all have to come in within 5% of predicted failure. So just, you guys hit 300, but you know, so just think about that for modeling. And so I'm going to predictions. I saw that you had only done 2 thicknesses, 1 millimeter and 2 millimeters. And so it's very hard to model what's going on with just 2. Why did you stop at 2? Because the material was not available, or what? Yeah.
That's an excellent question. Thank you so much. So it was both because we were limited in budget and time specifically, also in regards to the materials. But these were the thicknesses that were chosen for this presentation, especially due to the time constraints for this presentation. Outside of this, we did test several thicknesses, including 1.33, 1.66, between 1 to 2. We also tested smaller than 1 millimeter and found that welding those was much harder and wouldn't produce good results, which is why we stuck between 1 millimeter and 2. We knew that increasing beyond 2 would just lead to a higher payload and weight, and it wouldn't be probably as efficient as we would like it to be, which is why we constrained between 1 and 2. For the sake of the presentation, we only included those 2.
So I think we're getting a lot of questions that have the common theme, which is what are the levers that we're pulling to control what our final shape is, control reliability. We made sure to not go too far into having too many variables so that we could truly understand the fundamentals of what's happening here. So we chose 1 and 2 millimeters because they were, first of all, readily available. But also, if we stuck with 2 thicknesses, we could focus on the shape and understanding how it buckles. We didn't know how it buckled at 9 months ago. Now we understand how it buckles, and now we know how to control that. So I think we've been all saying a great future step is now expanding our variable space a little bit more and looking at maybe like a 3 millimeter thickness or even thicker if we want to up our pressure.
Yeah, actually, personally, I really like this concept. It's innovative. So you can inflate and rigidize the structure. So that is the great point. And you mentioned you test only 2 millimeter thick the specimen because some supply issue. But I'm wondering what's the maximum thickness you can inflate using the technology, because the current cryogenic tank, we have three different the material. One is the stainless steel, the metallic, or some metallic, the inner layer composite, polymer composite, or the entire polymer composite, the structure, but much thicker than 2 millimeter. So I'm wondering if you can inflate more thicker the plate.
We can definitely inflate a thicker plate. At that point, it's a matter of being efficient with our weight. So we can, it's also a matter of equipment capability. So if you've got a 6-inch diameter module that's 5 inches thick, you're gonna require a heck of a lot of pressure to inflate that. If you have an 8-meter wide inflatable that's 5 millimeters thick, you're not gonna require nearly as much pressure, but you are gonna require it a little bit more. So it's definitely a careful balancing act of what is the optimized thickness, what is the optimized diameter, what's the optimized radius, all of those variables, so that we can not only provide a relevant solution in terms of combating the environmental hazards, but also making sure we're efficient with the space on our rocket.
Do you guys want anything?
Also, as much as I hate to admit this, welding ability was definitely also a big constraint and a limitation in how we built this, since a lot of the times we had to weld them ourselves. But that is also definitely something that also highlights how this technology can definitely be improved on in the future, and also the capabilities of this technology. Since with us welding, starting to learn welding and being able to weld our own inflatables ourselves, definitely having a third party that is a lot more consistent with the welding and can try a lot larger design space, such as a bigger radius and higher thicknesses, and also even maybe some thinner sheets. Using that would just already incredibly increase the capabilities of this technology, and that's definitely something that can be improved on, as this technology keeps on moving forward.
Yeah, I just want to summarize real quick about how these variables affect our deformation. So when we increase the radius, the required pressure decreases, and then when we increase the thickness, the required pressure increases. So what Trevor was talking about before, balancing those two, is something that we'd like to explore more at larger values, so above 4 feet and above 2 millimeters.
All right, yeah, a little bit in line with that. One of the things that you had mentioned in there, that you need to bury these 40 centimeters right under the surface to kind of give yourself that advantage. And then, as you mentioned, there's this idea that you can go up with bigger and bigger tanks. So this is more of a thinking about this at a system level. You mentioned in there briefly at the beginning, you need an autonomous lunar excavator, something to put it in there, take it off the lander, move it out, put it down, inflate it, run the lines out, connect the lines. There's a lot of other systematic things that need to be involved in it. And one of those is also, when you're burying it, if you have a huge tank, you obviously have to dig deeper to do that, right? So one of the other things you can think about is maybe having a smaller one or a series of small ones that are all buried at a shallow depth, or what you need, makes more sense in some of those cases. And then as a separate question, you also mentioned here that you need, I guess, ideally you want the thing to be a little warmer, right, when you inflate it, so that you don't overstress things. And you had mentioned, using solar heat to do that, laying it out. So the only thing I would caution there is, because we've done some structures like this where you try and heat it in the sun and it's metal, it's yes, it absorbs that very quickly, but it conducts it away very quickly. So it may not do exactly what you think it does there without some additional insulation, but something to consider.
Yeah, I think to that point, it was more so that metal becomes very strong. I think stainless steel specifically might become close to 2 times as strong when it's cryogenic. So it's more of a difference of cryogenic versus roughly room temperature. I would certainly have liked to try pulling one right out of the oven and heating it up to see if we got some really high deformation. However, most of these experiments were done at room temperature or maybe even slightly colder because we're located in Chicago. So I think there's no worry about as long as you're at these, in this lunar daylight where you're seeing over 25 C.
Yeah, I love this. It's so cool. Your concept is really interesting. But I'm also mad at you because I don't understand how you guys thought you could do your welding yourselves. This is my fight with every single vendor. Welding needs to be done by certified welders and is inspected by certified weld inspectors. So the ambition is good, but how are you going to tackle that in the future? Do you have a certified weld inspector at Northwestern, somebody that you can consult? There's also no need for, somebody mentioned that you want to build a standard on how to, there are standards already by NASA on welding. So if you want to chat about that, I can give you, but this is great. It's just that the welding, the manufacturing, it has to be done by certified weld inspectors.
I totally agree with you. One of the biggest challenges, if not the biggest challenge we have with this project is ordering through and getting processing done. We've got some big bureaucratic giants. So we wanted to do some more welding with our partner, IMS Manufacturing. They are a worldwide metal manufacturing company. They have professional welders, certified welders, and weld inspectors there. And we think that we can achieve the best results with a company that does the scale that they do, since this is their everyday job. So at this point, we've set up a really good relationship with them where not only are they giving us at-cost welding, but they're also, they know exactly what we want and how we want it. So we can send them over a DXF file and ask them to weld it with certain material, and they'll go ahead and do that. I will also add on here that another issue we had is initially they did not know how to weld these very well. So some of the earlier modules that were manufactured had some visual defects that I think speaks to how resilient this technology is even with some visual defects, we're able to get, I would say, relative consistent data with at least the shape of our inflation. And if we can fix those with a weld inspector, I think we're going to be in a good place.
I'm not mad at you. I'm just saying this is great. Yeah, again,
These are all going to disappear before the end of them.
Yeah, I may take one. No, it's a lesson. I'm just saying this is not a unique issue. You guys are phenomenal, you're students. I have to deal with companies that think that their manufacturing people can do welding. It's a very tricky thing to do. So I applaud you. I bet that even the ones that you tried yourselves was good. And hopefully you followed welding safety. I'm not gonna ask.
We did.
And I'll get all nervous, okay? But yeah, excellent job.
The standard in most of aerospace is probably friction stir welding at this point. I imagine building this for the moon, that's what you do, but
Yeah, that's
you
when I
guys
come
didn't
in.
have a friction stir welder just sitting around.
Actually where we want to go. So we did look at aluminum, because you may be wondering, what about other materials? And we love aluminum. We want to do aluminum. The problem with aluminum is we did not have access to friction stir welding, so we were using filler material. And filler material in aluminum is very porous and brittle. So the aluminum would deform, but the second you got to a certain point with your weld, it would burst open. Friction stir welding, we think we can fix that. And we still have favorable properties at cryogenic temperatures, but we save some of the weight.
As an ISRU guy, I'd just like to point out that the moon is covered in aluminum, but there's no steel there. So if you're going to make them locally, you probably want to do that out of aluminum.
Yeah, unfortunately, friction stir welding gets expensive pretty quickly.
Do we have any other questions from the judging panel? Brian.
As far as a lot of inflatables, pressurized pressure vessels, you do proof testing for them. Do you see a path to proof test these and repackage them down to their state, or do you see more risk in that than it's worth? What are your thoughts there?
I think that's actually an open question. One really cool property we found is when we crushed them down, we were able to actually inflate them up back to their original deformation, but with lower pressures. So that's a possibility, is crushing them down and then inflating them, because we know it doesn't impact the seal. The other thing is our X-ray tomography. So if we've got a big enough X-ray tomography machine, I'm sure there's one out there, you could just put the whole thing in the machine and run a CT scan. We also discussed with IMS manufacturing some other methods that they use. A lot of industry methods are a little bit more challenging with weld characterization, since you need access to both sides of the weld. But there's some thoughts about putting some dye in there and looking if using that dye to see whether or not there's any pores.
I'll just add one more thing. Unfortunately, I think crushing it down wouldn't be the best idea, in that you might start some big crack propagation and have very low cycle fatigue that you would rather want to avoid with a pressure vessel. But I would say that our technology seems to really beat out a lot of the other pressure vessel technology in terms of, especially we can do aluminum, how much you can store in a certain weight and volume. So if you do very high reliability testing, like Kevin mentioned, then maybe having 1 or 2 small modules not be perfect once they arrive on the moon wouldn't necessarily be detrimental, and you can statistically make sure that a certain weld length will be very reliable.
And that was perfect time. You guys hit both of your 0 marks on perfect time. So thank you, Northwestern. Let's give them a round of applause.